So yeah, that was a lovely introduction. My name is Makemake. Some of you might know me from Twitter or as the guy who hacked Uvo Finance. I've been writing code for quite some time. Before crypto, I've been doing threat security stuff, hardware and binary exploitation and reverse engineering. I've been writing Rust for the past 3 to 4 years. And I'm currently working at Phylax, where we do app-defined security enforced by networks, which is a fancy name for hack prevention. So, in this talk, I'll be covering the role of block builders, how we use them at Phylax, some tips and tricks for building your own block builder. So the tips will generally be around making your block builder more performant and not about extracting MEV, as that's not really what we do at Phylax. So enjoy. To understand how transactions land on the blockchain, we have to understand how the flow from sending the transaction to getting it to the blockchain looks like. So we have a funny meme explaining the life cycle of a transaction on mainnet. So on Uniswap, you would click the swap button. This will get sent to the mempool, then relay to the builders, and the builders will compete in a builder auction for extracting the most MEV, and it will finally land on mainnet. At Phylax, we deal with building blocks for L2s. So this will look different from the order flow of this happening on the L1. So keep that in mind. A key difference is that on L2s, we don't have multiple proposers or a public mempool. And this means that the sequencer is the one including everything and holding all of the transactions. Thankfully, OP Stack is architectured very similarly to Ethereum. We have OP Node, which acts like the consensus layer, and we have OP Gas or RAT or whatever, acting as the execution layer. So what we can do to get an external block builder is we use a tool called Rollaboost made by Flashbot, logo here, to proxy the connection between the execution layer and consensus layer and forward the engine API calls to our block builder. So we have pretty much what's happening here. We have an engine fork choice update, which we proxy via Rollaboost and send it to our builder, which is the sign for our builder to start building a block, basically. And then OP Node will request a block via engine get payload. And then we have 150 milliseconds to respond with a payload. And if everything goes according to plan, we have successfully built a block with an external builder. So on a Phylax protected L2, the lifecycle of a transaction looks something like this. It gets sent via the RPC to the sequencer. It will then be inside of the sequencer and shared to the builder mempool. The builder will build a block with the transactions inside of its mempool. And the transactions will be included in the canonical block on the L2 if all of them are fine and well. So, on the inside, builders selectively order transactions inside the blocks to maximize value or perform some other task. So on the L2, we don't care about maximizing value, as that's zero sum and generally negative for users. We more care about other productive use cases we have. So some of these include WorldCoin's human prioritization, flash blocks on a unit chain, and of course, Phylax hack prevention. To better explain what I'm going to talk about for the rest of this talk, I'll need to introduce you to what Phylax is and how the Phylax credible layer works. So the credible layer basically enables the apps to define states they don't want their protocols to be in. Think of it like invariant tests in Foundry. You as the developer can write assertions which are similar to Foundry tests, and we make sure that transactions that invalidate said assertions never get included on chain. And for example, if they are force included, we have other methods of making sure that they don't cause damage. So we protect against that as well. What does an assertion look like? So here we have a basic example of an assertion that checks for price oracle deviation. We get the price of the token before the user begins a transaction, and we define a maximum range that the price can move in one transaction. Keen-eyed among you might have noticed that we have, you can see a PH fork pre-state and PH fork state. And those are part of the assertion syntax. So we have a special EVM called the PH EVM, and we have additional precompiles or cheat codes inside of it. And those allow us to do things like arbitrarily forking the state, reading storage slots of external contacts that don't have getter functions, reading logs of your transaction, getting like the call inputs, and much more. So yeah, and this all happens like during block execution, like as soon as like the regular transaction gets executed. If you're interested to learn more about this very cool primitive, I'd say, there's a QR code here. You can scan it, and that will lead you to our docs, where you can find the assertion book, where you can see what assertions can do, and even write your own assertions and include them as part of your unit tests. I'll leave it up to screen for a bit. Yeah, okay. So to achieve real-time hack prevention, the number one thing we need is performance. The Phylax builder cannot be a major performance downgrade from the default sequencer setup that's not running any assertions. We need to be real-time. And when we do run assertions, we need to be able to execute as much gas as possible so we can perform all the checks with set assertions. There's no point if we just like, run a million gas after each transaction. Nobody's going to use that. If you don't get those two right, there's no point to this. Networks won't integrate, developers will not want to use it because it's too limited and they cannot perform the checks they otherwise would want to perform. So Phylax, which is our block builder, manages to do upwards of 2.4 gigagas per second. To put this in perspective, that's 828 full Ethereum mainnet blocks worth of gas for every transaction that lands inside of a block. With a full 40 million block of just regular user transactions, we are able to execute an additional 2.4 gigagas worth of compute. And this is just like the MVP. We are just like beginning. We can squeeze more performance out of it, and we are consistently working towards doing that, and we know how to do it. So now to answer the question everyone here is for, what makes it so performant? Even though it would be very nice if it existed, there is no silver bullet for performance. To build performance software, you need to be constantly monitoring and profiling the code you write. When designing access methods for data structures, databases, systems, whatever, there generally exists a three-way trade-off: read, update, and memory overhead. If you choose to optimize two of the above, the third one will suffer. That can either be through contention or coherent cost. So for example, if we focus on read and update overhead, we will have to use a lot of memory. If we want to optimize for update and memory overhead, that means that reads will suffer. We will have to use locks everywhere. And you get the point. And updating means just like writing. So read, write, memory. Memory, like how big your data structure needs to be. Yeah. Humans are generally really bad at guessing where performance is lost. So eyeballing is generally not going to do it. Flame graphs, tracing, perf, deletion profiling are some tools you have at your disposal to gauge the performance of your program. Optimization is an incredibly difficult job. Large companies have like entire teams just dedicated to like optimizing their software. You can generally get like 95% of the way there if you have like, I don't know, if you use like the tools from the above and I don't know, have like a beer, Zens, and like faith in God with you. So we could be here all day discussing like the intricacies of like how to optimize software, how to like, optimize data lines, caches, whatever. But to make it short, I recommend reading the SLED Theoretical Performance Guide. It's an amazing TLDR of what you need to actually focus on when you're dealing with IO-bound systems and how you are supposed to benchmark them. So let's get into some of the things we did at Phylax to improve our performance. In Phylax, we basically have two modes of execution. We have the regular transaction execution, and we have the assertion execution. We execute transactions sequentially, and then run the assertion EVM code in parallel. We can do parallel execution for assertions quite easily because assertions do not modify any state of their own. They just execute code, and we only care if they revert. If they did revert, that means that the assertion has failed, and we have to throw out the transaction that triggered the assertion that caused it to revert. When designing data access structures, we kept in mind that we need extremely fast multi-threaded read-only access. The design we ended up landing on was the overlay DB. It keeps a large in-memory cache of EVM state, and it has an underlying database, which in our case is the Rat database. it will first read the cache, and if the state is not in the cache, it reads the rat database and puts it in the cache. The cache itself is a buffer is tiny LFU data structure. But what that means is that when data comes in, it lands in a buffer, and we will periodically have a job that removes things from the buffer, puts it into the cache itself, and evicts any cache that needs to be evicted. And we do that when we are not building a block, so we don't have like that kind of contention when we build a block. The reason for just not relying on RAS and the operating system, because that's also a thing. When you have a lot of like disk access, the kernel will at some point use unused RAM to cache your data. But we don't do that because we want control over it. We want to know exactly how much state we have in RAM, and we want it to be reliable. It also gives us the flexibility of being able to like change the data structure we have quite easily. So if we, for example, want to store like 16 storage slots in the past, we can do that. Okay. We were then presented with another problem quite quickly. Because of the way that gives us database access, we were essentially limited to a mutable reference of the database, so we had to get quite creative. What we ended up doing was building the active overlay database. It is essentially a wrapper over a mutable revm database to turn it into like a non-mutable database ref. The end result was a data structure that was like 64 bytes large and did everything we needed. We got fast data access for as little complexity as we possibly could, and fast cloning across multiple threads. We have just today, and I believe like an hour and 30 minutes ago, open sourced the repository on GitHub, which contains all of this code and data structures. So you can go ahead and look at it now. I unfortunately don't have it in the slides because it was done like an hour ago. But yeah, if you go to Phylax Systems GitHub, you'll be able to like go into the assertion executor repo, and you can investigate both of these data structures to see what makes them so interesting. Yeah, early on, we got nerd-sniped into building our own database, and what would essentially be a blockchain client from scratch. How it worked is we were performing an ETL pipeline from Rat's MDBX database to SLED. And why we did this, I'm not quite sure. But some block builders had this approach, so okay, we said let's see what happens. Rat then very quickly updated their database schema. It broke our pipeline completely, and we very quickly realized why it was a bad idea. So we have this mending repository that's like the ETL pipeline. We have the shared DB data structure that was the data structure we were planning to use for our database, which held like an in-memory cache and like an FS file system database thing. And then we had like the function to do the ETL. So yeah, yikes. Optimizing the actual EVM transaction execution is incredibly difficult. You're not going to be optimizing the EVM execution code beyond what is already in Revm without spending literal months for like maybe a few percentage points here and there. Revm is a very well optimized piece of software already. What you can, however, do is reduce the time you spend on processing transactions. Do you need to recover the signer, for example? Okay, amazing. You can do that in parallel to other jobs that you do. So I don't know, while you're executing like the sequence of transaction, you can like do cryptography on the transactions you have already that are sent by users. It saves you a lot of time. Pipelining all of these things for us saved us around like 5 to 10% in performance. Alt L1s don't want you to know this, but the bottleneck for scalability is actually I/O. Only when we get to a certain point where we optimize the data structures enough so that I/O doesn't matter, does it make sense to pursue parallelism. And parallelizing the EVM is very difficult. It is inherently a sequential piece of software. Executing state change transactions in parallel means that some transactions will inevitably work on conflicting data. And what that happens is you have to like, at worst, like throw out your parallelized work and do it sequentially. And that's really not ideal because you're throwing away work and you have to re-execute the block. State access lists don't always work because a transaction before another transaction might change something, and that transaction impacts something else along the lines, and when you are processing that transaction, the state will change. So it gets quite complicated. So we solved this very easily. There is no state. I love you. So if you remember the transaction flow, we execute the transaction, and then we have a bunch of EVM code we have to execute to verify said transaction's validity. Assertions cannot modify state. They are completely read-only. So what we do is just throw set assertions into a thread pool, and we basically call it a day. We have a ring parallel iterator, and we join the results on that, and amazing, everything is happy, and everything works. A fun property of Rust is that you have multiple different allocators at once. It's kind of like a Zig in that regard. So this means you can easily use arenas, and you have custom allocators for said arenas. So arenas are pre-allocated regions of memory that are reserved for upcoming data that you know you will use, but that you don't have now. The rationale is that allocating things in advance reduces constant allocations of memory and freeing some memory as the memory requirements of your program grow at runtime. So you will just allocate instead of doing tiny, 1 megabyte allocations every, whenever, you will allocate 1 gigabyte, and then you will assign that memory inside of the arena. When we're dealing with thread pools, for example, Rust really likes to allocate and then free memory as soon as it goes out of scope. And this can be very bad for performance, which is why we use arenas. And I have two here. I have a sharded slab, which is a lock-free parallel arena for memory, and I have GC arena, which is basically like arena but garbage collected. And it's kind of neat. So thank you. That's pretty much it. Thank you all for listening. I don't want to get too much into details to not bore you all. If you have any specific questions, I'd be very glad to answer them. We will be open sourcing our builder quite soon, and we will have a public devnet in the coming weeks. So make sure to follow us on Twitter for updates at Phylax Systems. And we are also hiring. So if you are interested, let me know after the talk. We have Rust and DevOps positions open. So yes, thank you all.
Okay, let's start with questions. There is one there.
Hello. A general question about Phylax.
Mm-hmm.
Where are the assertions stored? So I deploy a protocol, and I want to assert that my protocol never reaches this certain state. Where do I publish these assertions so that the block builder can use them?
Yeah, that's a great question. So the flow basically goes like this. You will we have a command line tool called PCL, and you would use that within your Foundry project to write set assertions, and you will use it to test them. Once you are confident that your assertions are sound, you would use PCL submit, which will submit the assertion to what we call the assertion DA, which is the DA layer for these assertions. The assertions will be stored there, and when you submit a transaction on chain to activate the assertion and assign it to a contract, you will also, because you also have to prove the ownership that you are the owner of that contract. You cannot arbitrarily add assertions to any contract, right? So when you do that, the builder will index them, and after a time lock has passed, after finality, these assertions will become active, and they will start to be enforced.
And a question. Just so Phylax is a block builder that will make sure that transactions that land in a block respect these assertions.
Well, not necessarily. So we offer the block builder ourselves, but it's up to the networks to run them. So we provide support. We do everything we can to support them. However, but it's up to whatever L2. I can't say specific names for obvious reasons, but it's up to the L2 to actually run it.
And to promote the usage of this.
That's also on us.
Great, thank you. Any other questions, if we have? Okay, no takers? Well,
I've blown everyone away.
yes. Well, thank you so much.